Hello and welcome to Earth Science Lecture 28, The Reason for Seasons. Nearly all the energy that drives Earth's variable weather and climate comes from the Sun. Earth intercepts only a minute percentage of energy given off by the Sun, less than 1/2 billionth. This may seem to be an insignificant amount until we realize that it is several 100,000 times the electrical generating capacity of the United States. Solar energy is not distributed evenly over Earth's land and sea surface. The amount of energy received varies with latitude, the time of day, and the seasons of the year. Contrasting images of polar bears on ice rafts and palm trees along a remote tropical beach serve to illustrate these extremes. It is the unequal heating of Earth that creates wind and drives the ocean's currents. These movements of air and water in turn transport heat from the tropics toward the poles in an unending attempt to balance energy inequalities. The consequences of these processes are the phenomena that we call weather. If the sun were suddenly turned off, global winds and ocean currents would quickly cease to exist. Yet, as long as the sun shines, the wind will blow and weather will persist. So, to understand how the atmosphere's dynamic weather machine works, we must first know why different latitudes receive varying quantities of solar energy, and why the amount of solar energy changes to produce the seasons. As we will see, these variations in solar heating are caused by motions of the Earth relative to the sun, and by variations in the Earth's land-sea surface. Earth has two principal motions, as we discussed in our previous lecture: its rotation around its axis and its orbit motion around the sun. The axis is an imaginary line running through the planet's poles. Our planet rotates on its axis once every 24 hours, producing the daily cycle of daylight and darkness. At any moment, half of Earth is experiencing daylight and the other half is experiencing nighttime. Each year, Earth makes one slightly elliptical orbit around the Sun. The distance between Earth and the Sun averages about 150 million kilometers, or 93 million miles. Because Earth's orbit is not perfectly circular, however, this distance varies over the course of a year. Each year, on about January 3rd, our planet is about 147.3 million kilometers, or 91.5 million miles away from the Sun, which is closer than at any other time, a position known as perihelion. But about 6 months later, on July 4th, Earth is about 94.5 million miles away from the Sun, which is the furthest at any other time, and we call this aphelion. Notice that the seasons of Earth are caused only by the tilt of the axis, and not by any change in Earth's distance from the Sun. Although Earth's orbital distance varies over the course of each year, the variation is actually really small. If Earth did not have an axis tilt, we would not have seasons. Earth is only about 3% further from the Sun at its furthest point than it is at its nearest. This difference in strength of sunlight is so small that it is easily overwhelmed by the effects caused by the tilt of this planet. So you know that we have seasonal changes, such as longer and warmer days in the summer and shorter and cooler days in the winter. So again, why does this occur? Well, the reason is because we have our planet being tilted on its axis of rotation, and it's not perpendicular to the plane of its orbit. So instead, the axis is tilted by 23.5 degrees from the perpendicular. In other words, from a vertical line, instead of it spinning straight vertically, it's tilted by 23.5 degrees. For example, on one day in June each year, the axis is such that the northern hemisphere is leaning toward the Sun by 23.5 degrees. In December, 6 months later, when Earth has moved to the opposite side of its orbit, the northern hemisphere is now leaning 23.5 degrees away from the Sun. On days between these extremes, Earth's axis is leaning any amount less than 23.5 degrees from this vertical motion. Note that the Earth maintains this tilt as it orbits the Sun, so its tilt doesn't change drastically from time to time or location to location. So Earth's North Pole is always pointing in the same direction throughout the year toward Polaris. So the reason that we have these different seasons is because we orbit the Sun with a tilt. Occasionally we're tilted toward the Sun, and sometimes we're tilted away from the Sun. So let's go ahead and discuss what happens as a result. If the variations in the distance between the Sun and Earth are not responsible for seasonal temperature changes, well, it's the tilt that's causing it. As we move from summer to winter, the angle of incoming sunlight decreases, and the path of the Sun in the sky shortens. This is the reason for the seasons. So in summer, the Sun is not only high in the sky, but it takes a longer path. In winter, it's low in the sky and takes a short path. So why does this matter? Well, let's take a look at this in a little bit more detail. The northern hemisphere is tilted toward the Sun in the summer. For our summer, it's winter in the southern hemisphere at the same time. The northern hemisphere spends more than 12 hours in the sunlight. Thus, the days are long, and it's summer in the northern hemisphere. The Sun is high in the sky, and so sunlight is striking the ground at nearly perpendicular angles, which heats the ground efficiently. During this same time, in the southern hemisphere, days are short and nights are long. Thus, it is winter in the southern hemisphere. The steeper sunlight angle makes it summer in the northern hemisphere for two reasons. First, as drawn in this zoom out, the steeper angle means that more concentrated sunlight, which tends to make it warmer. Second, if you visualize what happens as Earth rotates each day, you'll see that the steeper angle also means that the Sun follows the longer path through the sky, giving the northern hemisphere more hours of daylight during which it can be warmed by the Sun. So we can revisit this image on the previous slide. So the Sun is higher in the sky, so it's giving us more concentrated sunlight, and it's up in the sky for a longer period of time. So that means more time to heat. Well, the opposite is basically true for winter. Half a year later, the situation is reversed, with winter in the northern hemisphere, which is now tilted away from the Sun, and summer in the southern hemisphere. The Sun is low in the sky now, so sunlight strikes the surface at a grazing angle and causes little heating relatively. During spring and autumn, the two hemispheres receive roughly the same amounts of illumination from the Sun, and daytime and nighttime are of roughly equal length anywhere on Earth. The sunlight angle gradually changes as Earth orbits the Sun. In between these two extremes, both hemispheres are illuminated equally in March and September. It is therefore spring in the hemisphere that is on the way from winter to summer, and fall for that which is going from summer to winter. So I usually get from students questions on why the angle really matters. So I say it means more concentrated sunlight versus this situation, or vice versa, but what is the reason for that? Well, hopefully this graphic can help depict this. In summary, when the Sun is directly overhead, the solar rays are most concentrated and are thus most intense. At the lower angle, they are more spread out and less intense, so you get less heating as a result. So the way I like to show this is, imagine you have one patch of sky, so let's say it's this length wide. Okay? So in order to heat that same area here, you have 1, 2, 3, 4, 5, 6. So 6 imaginary sun rays coming into the same area. But now when you tilt them, only 4 rays are touching that same area. And then you tilt them even more, and now there's only 3 sun rays coming in. So here you have more heating for the same area than you do when the angle is very shallow. And so this is a reason why we talk about this concentrated sunlight. Historically, 4 days each year have been given special significance based on the annual migration of the direct rays of the Sun and its importance to the yearly weather cycle. On June 21st or 22nd, Earth is in a position such that the north end of its axis is tilted 23.5 degrees toward the sun. At this time, the vertical rays of the sun strike 23.5 degrees north latitude, a latitude known as the Tropic of Cancer. For people in the northern hemisphere, June 21st or 22nd is known as the summer solstice, the first official day of summer. So here is an example of this. So the Earth is tilted toward the sun, and so the angle of the sunlight is more steep in this case. And as a result, we get our warmer days. We'll take a look at the Tropic of Cancer discussion more in just a moment. 6 months later, on about December 21st or 22nd, Earth is in the opposite position, with the sun's vertical rays striking 23.5 degrees south latitude at a line known as the Tropic of Capricorn. For those in the northern hemisphere, December 21st and 22nd is the winter solstice. So we have the summer solstice and the winter solstice, when we're tilted most toward or away from the sun. And here's just a random image I wanted to throw in to help show this. So in winter, the sunlight's coming in and striking the southern part of the Earth, so it's warmer down there. But in our summer in June, the sunlight is coming in more steeply over the northern hemisphere where we are. So we experience summer as a result. So we just discussed the solstices, so when it's the first day of winter and first day of summer, but what about the equinoxes? Midway between the solstices are the equinoxes. September 22nd or 23rd is the date of the autumnal or fall equinox in the northern hemisphere. And March 21st or 22nd is the date of the vernal or spring equinox. On these dates, the vertical rays of the sun strike the equator, which is 0 degrees latitude, because Earth is in such a position in its orbit that the axis is tilted neither toward nor away from the sun. And I'll actually step back for a moment, quite a bit. So here, on our equinoxes, it's spring and fall in these two cases. We're not tilted more toward or away from the sun. So we're in fall or spring as a result. The length of day versus darkness is also determined by Earth's position in its orbit. The length of daylight on June 21st or 22nd, the summer solstice in the northern hemisphere, is greater than the length of night. The opposite is true for the winter solstice, when the nights are longer than the days. The farther north of the equator you are on June 21st, the longer the period of daylight. When you reach the Arctic Circle, which is 66.5 degrees north latitude, the length of daylight is actually 24 hours. This is the land of what's called the midnight sun, which does not set for almost 6 months at the North Pole. So you can actually see that in this image here. So this is an image taken in the same area at different times throughout the day. And what you'll see is that even at midnight, the sun did not set. It sure gets low in the sky, but when you're up in that Arctic Circle, there's a chance that you'll see this, where the sun never sets, and vice versa. The Arctic Circle is the southernmost latitude, that is 66.5 degrees north, in the northern hemisphere, at which the sun can remain continuously above or below the horizon for 24 hours. The Antarctic Circle is the northernmost latitude, 66.5 degrees, in the southern hemisphere, at which the sun can remain continuously above or below the horizon for 24 hours. And so this chart here I thought was interesting just to throw in. So it shows latitude, so 0 being the equator, 90 being the pole, and it shows you the length of day. So we have a 12-hour day at the equator on the summer solstice, but by the time you get up to the pole, suddenly it's a 24-hour day and it lasts for 6 months. And so it's pretty interesting to see how this works. And then it shows you the same for the winter solstice. So as we know, the sun is changing its position in the sky every day throughout the year. Well, it actually takes a particular type of path every year, and it's known as the ANALEMMA. This composite photograph shows images of the sun taken at the same time of morning and from the same spot at 7 to 11 day intervals over the course of a year. The photo looks eastward, so north is to the left and south is to the right. Because this location is in the northern hemisphere, the sun images that are high and to the north represent times near the summer solstice, and the images that are low and to the south represent times near the winter solstice. This figure 8 shape that it creates is called the analemma, and it arises from a combination of Earth's axis tilt and Earth's varying speed as it orbits the sun. So you can tell when it's summer and winter in this photograph just by thinking about it. Here, the sun is directly overhead, it's much higher in the sky, and so you get more concentrated sunlight. But here, it's coming in at shallower angles. So it's winter down here, and summer more at the top. And so just as a closing statement, I threw in a chart that could be a really good reference for students. So this table summarizes the characteristics of the solstices and equinoxes for a location in the northern hemisphere. An examination of this table should make it apparent why a mid-latitude location is warmer in the summer, when the days are longest and the angle of the sun is highest, and the winter solstice facts are the reverse. The days are shorter and the sun is lower in the sky. During an equinox, which stands for equal night, the length of daylight is 12 hours everywhere on Earth because the circle of illumination passes directly through the poles, thus dividing the lines of latitude in half. In other words, a more easy way to say it, we're not tilted more toward or away from the sun. So let's go ahead and close this out with 3 questions. Question number 1, what causes the seasons? Okay, hopefully, since this is the only topic of this lecture, your answer is changes in the angle of the sun above the horizon. So note, I purposely didn't put tilt of the Earth in, just because I thought that would be a little too easy. So a gradual change in the angle or altitude of the sun above the horizon is the contributing factor to seasonal temperature changes. So remember, the sun is either high or low in the sky and takes longer or shorter paths. Question 2. When Earth is in a position such that the north end of its axis is tilted 23 degrees toward the sun, this is called what in the southern hemisphere? Okay, so this one's meant to be a slight trick as well. So we're tilted toward in the northern hemisphere, but I ask about the southern hemisphere. So the southern hemisphere is actually tilted away. So it's winter down there. And last but not least, question 3. How often each year would an observer standing on Earth's equator experience no shadow during the noontime sun? So think about this one for a minute, and we'll get to a response in a moment. Okay, so the answer is twice. In order for the sun to cast no shadow, it must be directly overhead. So this question is basically asking how many times is the sun directly overhead at the equator. As the sun's position on the celestial sphere slowly moves back and forth between the northern and southern solstice points over the course of a year, the noontime sun will be directly overhead for an observer at the equator only twice per year, on the spring and autumnal equinoxes, when we're neither tilted toward nor away from the sun. All right, as always, thanks for watching and have a great day.